This video will be a recap of logarithms before we get to doing derivatives of logarithms. So we'll start off with the definition of a log. Logs are usually in base 10, and something like this expression here would be asking you the question 10 to the power of what gives you 100. If you're familiar with your powers of 10, the answer to that question is 2. So log of 100 equals 2. And if you do want to double check that in a calculator or something, you can look at log of 100 and it is 2. So most log questions you can just cheese on a calculator, but it's a good idea to actually practice these so that you're familiar with how the logs work. This one, for example, would be 4, and this one 1 over 10. Well, it would be asking you 10 to the power of what gives you 1 over 10, and based on our index laws, that number in here would have to be minus 1. So the answer to this log is minus 1. And it's always a good idea to double check that this answer is actually right on your calculator, and it is, so your calculator agrees. Log of 1 is 0 because 10 to the power of 0 gives you 1. Log of the cube root of 10 would be a third because 10 to the power of a third is the cube root of 10. So a lot of these log questions are actually more revision of your index laws. Now, when we have different bases, we write it with a little number down there. So log base 2 of 16, so it would be asking the question 2 to the power of what equals 16. So the answer here is 4. Log base 4 of 16 would be 2, because 4 squared gives you 16. Log base 16 of 2, so this is 16 to the power of what would give you 2. Now, it's actually the fourth root of 16, which would give you 2. Because 2 to the power of 4 is 16. So those two statements there are sort of equivalent. Now, how do we write the fourth root of 16? That would be 16 to the power of a quarter. So the answer to this question here, log 16 of 2, this is a quarter to give you that answer. Notice that it's very closely related to log 216, which was 4. All right, moving on. Log 732 of 1 is 0 because 732 to the power of 0 would give you 1. That's the answer there. Now, ln, if you ever see that written, it's ln. This is the same thing as writing log in base e. And if you recall, e was a very special number. E to the power of 1 is 2.718. So log of e cubed is 3 because, well, e to the power of 3 would give you e cubed. All right, then we have our log laws. So plus becomes times. So this becomes log of 4 times by 3, which we can simplify all the way down to log of 12. Next one here, we got to use log laws on the first bit. So this first bit will become log of 4 squared. 4 squared is 16. So that will become log of 16 minus log of 8. And then the log laws tell us here that a subtraction will turn into a division. So this becomes log of 16 over 8. Plus turns to times, take turns to divide. 16 over 8 is 2, so this is log of 2. Now, if you're ever not sure about simplifying logs like this, what you can actually do is you can just do this on your calculator. So 2 log of 4, take log of 8. And you're going to get a pretty nasty decimal number. And then if you look at log of 2, that should be the same decimal number. So we know we've done the simplification right. Here we have log of 4 plus 2. Now, it's best to write these both as logs. So log of 4 plus log of something. Now, the short answer here is the number that you put in here is 10 squared. So that's 100. And we've actually seen this before. Log of 100 is 2. So you have to be a little bit cheeky with how you write it, but basically if you write them both as logs, the number you would want in this log is 100, because we know that log of 100 is 2. All right, now we can just use our log laws to simplify this. So this is log of 400, because you would times those numbers together. All right, something like this. Now I'm going to show you 2 ways to do this question. So I might grab a second copy of that. So the first way to do it is just sort of your standard log law first. So this would be log of x squared times x cubed times x to the 4. And then you can actually use your index laws here. So this is log of x to the power of 2 plus 3 plus 4. which is log of x to the power of, let's see, that would be 9. Now, if you want, you can use another log law here. So this 9 could come out the front, and you could get 9 log of x. One other approach you could do, just to sort of prove to ourselves that the log laws are consistent, is you could pull the powers out the front. So this one you could write as 2 log of x. This one you could write as 3 log of x. And this one you could write as 4 log of x. Now, if I've got 2 of a thing, plus 3 of a thing, plus 4 of a thing, well, that's going to give me 9 of that thing, 9 log of x. So you can see that even if we take an entirely different approach here, you actually do get the same answer. It's 9 log of x in both cases here, which is good news for our log law consistency. I do want to point out that this rule here, where you're bringing the 2 out the front of the log, it can feel a lot like differentiation because it's a similar sort of motion. It is not differentiation. Please don't get those two things confused, because sometimes you might think you've done a derivative and you actually haven't done it yet. All right, we're going to look at log graphs in general, and then hopefully after that investigation we can actually answer this question here. So let's open up our Desmos here. What I've done is just graphed log of x there. And then one thing to point out is that if we look at the graph of e to the power of x, those two graphs are sort of following the same shape there, so to speak. In fact, those lines are a perfect reflection over the diagonal line on the graph. But the point is, basically, the log of x graph looks like this one is a base, and then you can sort of make adjustments to this graph by changing these letters. So k here, because we're timesing the whole thing by k is like a vertical stretch, vertical dilation. B will be a vertical translation, which probably feels a bit unusual because normally with a vertical translation, it's like a plus d on the end, and then that would be a vertical translation. And that actually does work in this case. So for example, you could change the d value here to move it up and down, or you could change the b value here to move it up and down. But we tend to just not have plus d on the end there because we already get a vertical translation out of this b thing that we're moving around. And the fun thing you can sort of do with that is, if you make it small enough into the negatives, it actually flicks backwards, which is pretty cool. This c value will just move the graph left and right. And in general, when you're looking at graphs like this, you can look at whatever you're doing to x. If you do like a take c, wherever you see an x in an equation, that will have the effect of moving it left and right. So that's what those three little things do. Now, coming back to this question, and I guess the deeper question, why is the b a vertical translation? Well, we can look at this graph here. So I might just call this y1 and y2. So y2 is going to be using the log laws, ln of 3 plus ln of x. And you can see that with this, it's just something plus the original graph of y1. So depending on what that number there is, that'll just cause us to be adding or taking off a constant. So if we look at the general form of a log graph, which was looking like y equals k ln b of x takes c, we can actually sort of prove that b is a vertical translation. So essentially what we can do is we can not really worry about the k for now, so I'll leave that all out the front, but we can think of that bit inside as ln of b plus ln of x takes c. And then if we sort of expand it out with the k in there, you've got k log of b plus k log of x takes c. So this is, I guess, what you would call like your base point to the graph. And then you're just adding on some constant, which actually does depend on what b is. So that's why b is a vertical translation, because you're just adding on log of b. But I will note, coming back to the graph, when we do change b, let's suppose I've got this red line as a starting point, and we might look at this point at 4, which is going up just up to about 1.16. If I do change b up to 2, the graph does go up, but it doesn't quite go up by 2, and that's because you're logging the b. So b will affect the vertical translation, but it's not 1-to-1. Like if you increase b by 5, the graph doesn't go up by 5. And also, if you start messing around with k, that will sort of mess with the b value as well. So we'll move it up and down. It just sort of does it in a very strange way. All right, coming back to our original question, how are these two graphs related? So what you can say is that y2 is a vertical translation of y1 up by log of 3 units.